Concept 9, number 1, we're just going to find the derivative of the integral. So this is using the fundamental theorem of calculus. We are going to go ahead and, the way I like to do this is if I don't have just a simple x here, first I got to make sure I've got a constant here and some function of x there. If I don't have just a simple x there, I like to just put its derivative in right now. The derivative of root x is 1 over 2 root x times, and then we go ahead and let the root x replace the t. So I get 18 root x to the 5th power. At this point, I'm going to think of this as x to the half, and I'm going to think of this as x to the 5 halves. So when I go to my next step, I have 18 divided by 2 is 9. And I have x to the 5 halves divided by x to the 1 half. That's x to the 4 halves, or 2. So that's x squared. And that's number 1. Any questions there? Number 2 is the easiest one in this group. It's just plain old x. I've got my constant here. Derivative of x is 1, so I don't have to worry about it. So all I've really got to do here is just let the x replace the t. And I've got the square root of 8x plus 5. And we're done. Number 3 is a little bit like number 1. I've got my constant. The derivative of x to the 10th is 10x to the 9th times cosine of the square root of x to the 10th. Well, I need to simplify that square root a little bit. So this is 10x to the 9th. The square root of x to the 10th is just x to the 5th. Oops, let's get the cosine in there. And that's it. Pause right here. Any questions there? The derivative of sine is cosine times, we'll just go ahead and put the sign in for x. Which I should probably write as cosine t all over 4 minus sine squared t. And we're done. Make sure you have the right variable in this answer. The other ones you're replacing t's with x's. This one you're replacing x with sine t's. And that's it for concept 9. Concept 10 is the substitution rule. In this one we're going to evaluate the integral using the given substitution. So this one they tell us what to substitute with. They're very kind. So we'll just go ahead and do that substitution. So I'm going to recopy it here. I always do my setup down below my problem. So I don't want a y, I want a u. U, they suggest that we let 3x squared equal to u. And I'm going to take the derivative of both sides of this. So du is equal to 6x dx. So that's the derivative of both sides. I don't see a 6 anywhere up here to replace, so I need to get the 6 to the other side. I'm going to divide it. So that gives me 1/6 of a du is equal to an x dx. This is great. This is right where I want to be. I see everything up here now can be replaced, except for the cosine. Cosine's a function. That's okay. But I've got the x dx right here. That can be replaced. And I've also got the 3x squared right here. That can be replaced. So I can replace everything except for the general cosine function. So that's why we call this substitution. It's that replacement that's going on. So let's go ahead and write this integral again. I've got the 3x squared gets replaced with a u, so now I have cosine u. And the x dx gets replaced with a 1/6 du. Well, 1/6 is a constant. It can come out front. And then I have my du. So what we've done here is we've turned a fairly complex integral into a much simpler integral. Notice this was a product with a composite function. I had a function inside my function. This is way more simple. I just have one term and a simple u inside my cosine. So now I can just take the antiderivative of this. So the antiderivative would be 1/6 times whatever the antiderivative of cosine u is. The antiderivative of cosine would be what? Negative, or just plain old sine, right? Sine of u. And then I have plus c. Don't forget there's got to be some constant here, some unknown constant. And then just replace u. So we have 1/6 sine of 3x squared and then plus c. And we're done with number 5. We'll pause here. Number 6, we're doing the integral. This time they don't tell us what to choose for u. But I want you to look back at number 5. Notice that when we chose when they told us 3x squared was our u value, when we took the derivative, do you see the x that came out? Yeah, we all saw that. Notice that when you look somewhere else in the problem here, there's an x, right? That thing appeared somewhere else. So when you take u, make sure that when you take the derivative, that if there's a value of x that appears in that derivative, make sure that's somewhere in the problem. If not, pick the other thing for u. Okay? So in this case, I want u to be what? X to the third minus 8. Because when I take the derivative of that, I get a 3x squared. And notice that I have an x squared to replace. That's all good. That's a really good start. You should feel really confident at this point. 3x squared dx. I don't see a 3 to replace, a constant 3, so I got to get that to the other side. So that's going to be a 1/3 du equals x squared dx. So now the x squared dx is going to get replaced by 1/3 du. That's a straight replacement. And the x cubed minus 8 is going to get replaced by a u. We're ready to write our new function here. I've got the integral. Instead of x cubed minus 8 to the 4th, I've just simply got u to the 4th. Instead of this x squared and that dx, I've got a 1/3 and a du. So there's my substitution. And the 1/3 is a constant, so it can go to the front. I don't have to mess with it inside here and worry about what that antiderivative would be. Now we can just integrate. The antiderivative of u to the 4th should be 1/5 u to the 5th, right? Add 1 to the power, divide by the new power, and then we got plus c. The x cubed minus 8 goes back in for the u. We just unsubstitute or follow that chain around, follow that pattern around. So I get x cubed minus 8 all to the 5th power, and then divided by 3 times 5 is 15, and then plus c. There's my final answer for number 6. We'll pause here. Okay, concept 11, we're going to integrate by parts here. So that means we're going to use that u and the dv, and we're going to use the formula for all that. I need to pick u carefully, and then everything else will be dv. If I follow our Lie8, little insects 8, then u should be the algebra x. dv then is everything else that's left in the integral. So I have a sine 9x, and I have a dx. So that's the rest of the parts. Make sure you get all the parts represented when you pick u and dv. Now we work with these. I already have u, I need du, so I'm going to take the derivative of both sides. The derivative of u is du, the derivative of x is just dx. I already have dv, I need v, so I need to take the antiderivative of both sides of this one. So this one I'm going the other direction. The antiderivative of sine 9x would be negative 1/9 cosine 9x. If we take the derivative of this, we should get back to there. The derivative of cosine is negative sine, that's why I have a negative. And then I would have to follow the chain. The derivative of 9x is 9, that's why I have the 1/9 to take care of that, so it equals that when we get done. We'll pause right here and see if there's any questions. Can you hear? We're going to plug this in the formula. I'll go ahead and write the formula this time. It's uv minus the integral of v du. And I always set my setup work this way, always line it up in this order, so that if I forget this, I just remember, oh, it's this diagonal minus the integral of this bottom. uv minus the integral of v du. That helps me remember that, just always organizing it the same way. U times v is x times this negative 1/9 cosine 9x. So I'm going to write that as negative x over 9 cosine 9x minus the integral of all this, of v du. Well, this integral of v du has a negative 1/9 constant. I'm going to let that come to the front. So negative negative is a positive 1/9. And then I've got cosine 9x, and then, of course, the dx is still here for the du. Notice how we went from a fairly complex integral to a much simpler one in this part of it. Now I just got to finish this integral. So I got negative x over 9 cosine 9x plus 1/9 times whatever that integral is. Well, if I want the The antiderivative of cosine, that would have to be sine, right? Sine 9x. But I got to watch out for, though, what that chain would be there. So I'm going to actually need a 1/9 sine 9x. And don't forget the plus c here. There's always going to be a constant if we don't have points of integration. Just cleaning it up just a hair more. Negative x over 9 cosine 9x plus 1 over 81 sine 9x plus c. And we're going to stop right there. And pause for questions. This is another integration by parts. We need to choose our u and dv carefully here. I see algebra and I see exponentials. Algebra comes before exponentials in our little pattern here, so we are going to let u equal 2t. dv then is the exponential e to the 9t, and then the dt is what's also left. So we've got all the parts represented. There's nothing left up here that's not represented here in the parts. All right, we've got u, we need du, so we're going to take the derivative of both sides here. The derivative of 2t is just t dt. No, it isn't. What is it? Yeah, there we go. 2 dt. I've got du, or dv, this is a v. I need v, so I need to take the antiderivative of both sides. The antiderivative here should be 1/9 e to the 9t. And we'll pause here, see if there's any questions. Let's set it up here. This would equal u times v, which is 2t times 1/9 e to the 9t. I'm going to write that as 2t over 9 e to the 9t minus the integral of v du. Well, this integral, when I multiply these together, I'm going to have the constant 2/9. So I'm going to let that constant come forward, 2/9. And then I just have e to the 9t dt. Jump down here. This equals, this stays the same. Front term just kind of gets carried along. Minus 2/9 times the integral, or the antiderivative of e to the 9t. We've already done that. We did it right here. We already know that's 1/9 e to the 9t. Sometimes you get lucky and you've already done some work that you need again over here, and you just recopy it and go. Just don't forget the plus c at this point. So we're headed to a final answer of 2t over 9 e to the 9t minus 2/81 e to the 9t plus c. Oops, missed.